Okay. All right. Thank you for coming, everyone. So today's talk is Dynamic DNNs meets Runtime Resource Management. And our speaker is Layson. He's a fourth-year PhD student at the ARM ECS Research Center at University of Southampton in the UK. And his research topic is software and hardware co-design for efficient embedded machine learning. He has a specific focus on dynamic DNN and runtime resource management. Currently, he's also a CPU performance research intern at Huawei R&D in Cambridge. He obtained his master in systems on chip design at the University of Southampton and bachelor degree in electronic engineering at the University of Sheffield. All right, Slate, the floor is yours.
Okay. Can you hear me okay?
Yes, yep.
Yes, yeah.
Okay. So thank you so much for the introduction. And thank you so much for the invitation for me to have a talk here to talk about our works on dynamic neural networks and how we think the dynamic neural networks can play an important role in the runtime resource management. So first, let me talk a little bit about myself and our teams, our institutions. So my name is Lei Xun. I'm a PhD student at the University of Southampton under the supervision of Professor Jeff Merritt, Jonathan Hare, and Bashir Al-Hashimi. So Southampton is a world top 100 university and is the founding member of UK Russell Group. And our department, electronics and computer science, is top 3 in the UK, and we have a very long relationship with in Cambridge. And so basically, in 2009, my supervisor Bashir and a member, David Flynn from ARB, founded this research center. Also, we are kind of working under the umbrella of the International Center for Spatial Computational Learning. So this is a center that is funded by the UK Engineering and Physical Science Research Council. And as you can see that the member of these centers is really global. So in today's talk, I will be mainly talking about the 4 things. First, I will basically talk about what is dynamic neural networks and why we need them. Right. And then I will give a brief overview of how the dynamic DNNs are developed in the last few years. And thirdly, which is the most important part, is like how the dynamic DNNs can play an important role in the runtime resource management context. So basically, we think that if we combine the opportunities in software, which is the dynamic neural networks, and hardware, including things like dynamic frequency voltage scaling or task mapping, then we can have much more kind of the performance trade-off opportunities at the runtime. Finally, I will give a light touch on my opinion on the kind of the current bottleneck of the dynamic neural networks. You are welcome to ask me questions during the talk. So let's get started. So like running inference on mobile and embedded devices have several advantages. First of all, we don't need to, if we run everything locally on device, we don't need to connect to the internet to use the model, right? And because of that, we can have lower latency and better privacy. I think privacy is also an increasingly important factor in today's society, because if you say like the neural network applications running on the mobile devices, nowadays they take images or audios as input, right? So, but they are pretty much the most private thing to us. So we don't really want to upload everything to the server to do the processing, right? But on the other hand, these neural networks are pretty, computational intensive for embedded and mobile platform. If we don't optimize properly, we can have very slow inference time, and they are really power hungry. So we don't want to that a neural network can drain the battery of our mobile phone in 30 minutes, right? And also, like if a software developer, right, only targeting the high-end smartphones, which has a very good GPU, also NPU, then I mean the software itself can only reach a very limited number of users. That is what they now they want, right? So for software developer, they want to their application reach as wider audience as possible. So they needed to kind of optimize the model properly. So regarding the model optimization, so generally I think there are kind of two steps. This is probably a oversimplified pipeline, right? So I think first of all, we need to start with a good model, an efficient model. For example, like a mobile net v3 is very efficient for mobile platform. But I think what we really run on the platform is not the original mobile net v3, right? It is some kind of variant of the mobile net v3 that can meet the performance target on the target hardware devices. So to do that, we normally need to apply some kind of pruning or neural architecture search to find a variant of the backbone network that can meet this target. So this process generally is a trade-off between accuracy, latency, power, and energy. Now here I give you an example of how this process works. So this is a paper called NetAdapter from MIT. So basically this system has three components, right? The first component is the input network backbone and the performance target of the application. The second component is the kind of the performance measurement, like latency measurement, energy measurement from a real hardware. And we kind of use this measurement as the feedback to the system. And the third component is we apply filter pruning, right? We kind of use this hardware feedback to guide it, the extension of filter pruning. So basically we prune the network and we monitor the latency, the energy, right? And we stop pruning when the target is met. So the general idea is to compress the model to approximately the right size to meet the performance target on target hardware platform. So this is a figure I taken from the paper. You can see it is a trade-off between accuracy and the latency. So what we really want to do is we want to compress the model as less as possible, right? Because the more we compress the model becomes less accurate. So let's say if we want to have a model that is a model that is, for example, 10 millisecond latency. So what we really want is this point, right? Because it has, by the way, can you see my pointer?
Yes, yep.
Okay, so basically if the latency target is 10 milliseconds, what we really want is this point, right? Although all these points can also meet the 10 millisecond target, but they are less accurate, right? However, what we think the problem here is, now, as you can see here, it says that the data was collected on a CPU of Google Pixel 1, right? So our question is like, what is the frequency? What is the frequency here, right? If we running at the design time, right? We running the model at the maximum frequency, and we meet this 10 millisecond target. Can we also have this maximum frequency? Can we always have the maximum frequency at the runtime? The answer is normally no, because when the system running for a while, we will hit a thermal limit and the frequency will be dropped, right? But if we, let's say we don't choose, let's say if the maximum frequency is 2 gigahertz and we choose a 1.5 gigahertz, just to be safe, right? So we can always have 1.5 gigahertz at the runtime. But if you do that, you kind of end up with a kind of a less accurate model in the very beginning. So what we really want is really, we want all the trade-off. We want all the trade-off. So at runtime, when the hardware resources become less available, for example, when the frequency drops, or when, for example, the hardware is shared between neural network and other applications. So basically less hardware resources are available to neural networks. We can switch to a relatively smaller, faster, but less accurate model. But if we save all the models here, it can be very expensive, because these models are, each of these models are individual models, right? Although they are very similar, but they don't share weight with each other. So the memory footprint of all these models can be very large. And here I give you an example. So in here, the model A and E are compressed model on the maximum frequency, and no hardware sharing happens. And you can see that A and E are just under the required latency target. But at the runtime, right, when the frequency drops, or when the neural network is sharing applications, sharing hardware resources with other applications, you can see we can no longer meet this kind of the design time optimized target. Okay, this is why we need dynamic neural networks. So instead of having multiple individual models, right? Dynamic neural networks is like a Russian doll on this figure. We pretty much have multiple sub-networks that share weight. So we only need to store the biggest model configuration. At the runtime, we can switch to smaller model configuration. So to have the same kind of the trade-off effect. But because like most of the models are static, right? If we switch to a smaller model configuration, they just don't work. So in order to get this kind of working subnetworks, we needed to train a regular model. For example, MobileNet V2, MobileNet V3, ResNet in a special way, in special ways. Well, the first work I read is actually from Chai. As you can see in this work, the network is trained incrementally, right? So the step one is only train part A of the network and just ignore B and C, right? And the next step, when we train part B, because A is already trained, so we kind of frozen the weight in A. So it's like B is kind of grow the knowledge upon A, and we repeat the same process for C. So after the network is trained incrementally, we will have, in this case, 3 model configurations, which is A, AB, and ABC. Right? We have 3 different model configurations. At the runtime, we can switch to one of the configuration to meet different accuracy, time, or energy consumption target. And all these networks are sharing the same backbone, which is the largest, the full network. The other work is basically, I forgot to mention that this is basically a dynamic channel scaling, right? The other work I want to mention is slimmable neural network. This is probably one of the most cited paper in the past few years. So the idea of this is, well, instead of just generate a few subnetworks, this work wants to generate a many. You can see it generate many subnetworks. And the way they train this network is what they call sandwich row. So basically, in each training iteration, they train the largest one, the smallest one, and a random ones in between. And they do it in a multi-objective way. So they want to guarantee that each subnetworks can work individually, right? And you can see this is also a channel, dynamic channel scaling approach. And there's another word called the mutual net. The mutual net is very similar to the soluble neural network, but mutual net, apart from just considering the number, kind of a channel scaling, mutual net also considering the input resolutions. Basically, if you have like less channels, you probably won't need to have a very big input images. So this work actually doing both channel scaling and the input resolution scaling. So the network can kind of switch in 2 dimensions. So here I'm just showing a kind of extended pipeline. So first we need to train an efficient model backbone, like a mobile net. Okay. Then we apply platform-aware model pruning and fine-tuning, right, to get a variant of the backbone that can just meet the performance target. And in here, we could choose the maximum frequency as the kind of the proxy for the performance, right? But like I mentioned before, at the runtime, you may not be able to have this hardware setting. You may not be able to have this frequency level. So the third step is actually we can kind of retrain this model using the previously mentioned the dynamic neural network training method to generate the subnetworks. So these subnetworks generally are smaller than the backbone network. So they require less resources. They are smaller, they are faster, but also less accurate. So at the runtime, when the resources is not enough, we can always switch to a smaller configuration of the network, so that so we can always meet the latency or kind of the power target. But one issue here is, like you can see, like we need to do a lot of training, right? We first needed to train the network, and then we needed to do pruning and fine tune the network, right? And in order to get the dynamic network, we needed to train it again using totally different training pipeline, training method. So we think that this is a problem, right? It is quite expensive to do. And if we use neural architecture search to get the original backbone network, the neural architecture search is already pretty expensive. And if we needed to do it to kind of retrain the model, I mean, it's just a lot of headache. So what we can do, right? Well, what we think is, like we see, like as the field moving forward, we start to see once for all network, like this kind of super network. So the reason we want to have this pipeline is because the previous dynamic neural network papers only consider the backbone network to be static, like a mobile net or shuffle net, rest net, they are static. We apply a specific training method to generate subnetworks. But what if the kind of the state-of-the-art model already have subnetworks, like once-for model, right? So the once-for model is another work from MIT, Songhan Group. So basically, they train a larger model. In this specific paper, they also use MobileNet v3 as the backbone. They train the model use what they call progressively shrinking. So they first train the full model, then they fine-tune the model to support many subnetworks. And in this case, it's 10 to the power of 19 subnetworks. And you can see here the model can change in 4 dimensions: the width, depth, kernel size, and input resolutions. So compared to the previous method, which can only change width or depth, or maybe width plus input resolution, you can see that the network we get from once-for network is much more fine-grained, much more efficient, right? And this approach, this once-for progressively shrinking pipeline, is generally applicable to a different field. So in this once-for paper, they applied it to image classification. They also applied the same approach to machine translation, GANs, and 3D neural networks. So in here, you may wonder, like, if you already have a network with that many kind of the subnetworks, why we cannot just use it on device? The answer is that because of this large space, the searching a model at the runtime is not feasible. It's super slow. Like based on our measurement, searching a new model on embedded platform can take hours. Searching on a good desktop might take like 10 to 20 minutes, but on embedded platform, it definitely take hours. So here we kind of compare the dynamic neural networks and the once-for-all networks. So generally speaking, the dynamic neural network contains, generally speaking, less than 30 subnetworks for different accuracy and latency trade-off. And at the runtime, different subnetwork can be used for different hardware availability, right? But because like the way dynamic neural networks are trained, they can either, generally speaking, either changing the number of layers or changing the number of channels. So it's like a coarser grade. It's not, it's kind of not the most efficient configuration. For once-for-all network, it contains 10 to the power of 19 subnetworks, and it is more efficient than dynamic neural networks because it can change in multiple dimensions: input resolution, kernel size, number of layers, and number of channels. But because the search space is so large, if we do the search at runtime, it's not feasible. It's just too slow. So what we do is we kind of combine the idea of two approach. We propose dynamic FA, which combine the benefit of dynamic neural networks and also the once-for-all network. So this is what we do. Okay, this is what we do. So we use a pre-trained once-for-all network as the backbone, and we do the sampling. We do multiple sampling to get a small library of subnetworks, and this library, you can see that they have generally a trade-off curve, right? We have the model has large latency, generally more accurate, and less latency are generally less accurate. The reason we do the sampling for CPU and the GPU separately is because, like, based on the previous research, GPU and the CPU, they prefer different architectures. So this is also a problem with the previous dynamic neural network papers because, well, if you can only do layer scaling or channel scaling, then you can only be efficient for one type of hardware. But in this case, in the case of once-for-all, it contains all the subnetworks for all kind of hardware. The question kind of from how we generate subnetworks become, in this case, how we can efficiently sample the subnetworks from the once-for-all space, and we form them into a small library so we can switch at the runtime. Because we only keep, in this case, only keep 6 models for CPU and 7 models for, 6 models for GPU and 7 models for CPU. So at the runtime, we can do a faster switching. And well, as you can see here, here is a kind of the sampling figure. So the original once-for-all search algorithm only use the latency as the target. So if you say, like, if you set the latency to be 60 milliseconds, without setting the accuracy target, then the point you get tend to be this point. So these are kind of easy to find point. So what we do, because what we want to get, we want to have a library of networks that have a trade-off curve. So what we do is, like, we first added the accuracy as a constraint as well. So every time we do a search, for example, if we want to search 60 milliseconds, we want the accuracy to be above 78%. And also because the original kind of the once-for-all network, the search space is 10 to the power of 19. But if we want to high accuracy kind of the point, we don't really need to kind of search in this region. So we also modify the search space of the original kind of the search algorithm. So we can kind of more easier to find these high accuracy points. So generally speaking, after multiple sampling, right, we have a small library on the parietal front. We take this to form this library. And at the runtime, we also have some kind of runtime management to switch between different models. So here's the comparison of our dynamic OFA with previous works, including mutual net and 3 versions of scalable neural networks. And as you can see that our model is generally more efficient than the previous kind of state of the art. Another thing I want to mention again is that previous dynamic neural networks, they propose a special training method to generate subnetworks, which can be very expensive. And in our case, we only do sampling from the 1-to-4 space, which is much quicker. And if you think, so can we apply this kind of previous dynamic neural network training approach to 1-to-4 network? The answer is no, because like the reason the purpose of 1-to-4 network is you just train network once, right? Then you deploy it anywhere, right? But if you take a kind of the search model from 1-to-4 and then you reapply the training to that model, then you're kind of doing the opposite of the original purpose of 1-to-4. So which means like every time you find a model from 1-to-4 network, you needed to do the kind of retraining to generate subnetworks. So what we want to say here is this training process is kind of unnecessary as for the state-of-art models like 1-to-4, because it already have subnetworks. So the problem becomes how we can generate subnetworks to how we can sample subnetworks.
I have a question here. So
yeah.
On the plot on the left, how does the dynamic OFA compare to like model that's not dynamic at these latency targets?
Yeah. So so sorry, the point is not showing here, but we do have the point in our paper. So basically, our dynamic OFA is about 0.5 to 1% lower than the original OFA model, because after the OFA model find these subnetworks, it apply fine tuning to increase the accuracy. So that's basically the difference, because every time 1-to-4 only sample one model and apply fine tuning. But in our case, because we sample kind of like multiple subnetworks, so it is really hard to do fine tuning. The other thing I want to mention is we also needed to consider another dimension, which is the switching time. So in here, these are all dynamic neural networks. The switching time between subnetworks are generally less than 100 milliseconds. But for 1-to-4 network, the switching time is generally like 50 seconds. So if you want to do this at a runtime, we have to use a dynamic network rather than individual models.
Can you go into the switching time bit? Why does it why is it so much costlier for the OFA?
Why is what?
Why is it costly to switch models for the OFA?
Okay, because like if you want to, so I guess first of all, if you want to switch a individual model, you kind of need to load the kind of new set of weight. But in the case of a dynamic neural network, you only kind of move part of the weight. I think that's the difference.
I see. Okay.
Yeah, and also, well, if you just consider the naive once for all method, right? Well, if you want to change it to another kind of subnetworks to meet the new hardware resources or new constraints, you actually first need to do the search as well. You first need to find that model, right? So if you take that into consideration, if you want to find a model at a runtime, the process takes hours on embedded platform.
So you're saying the switching time is bigger because you're also doing that search. So with your dynamic OFA, it would be a lower switching time. Is that correct?
I mean, in two ways. So if you do the search, the switching time, if you including the switching, the search time in the switching time, then the switching time will be hours to search and switch to a model.
Okay.
But if
so
you
the 50 milliseconds, I think you said, though that does not include the search time then, right?
Yeah.
So you
so 50 seconds is basically what I mean is like if you trade each individual model, each subnetwork as individual model, right? Then you can retrain, fine-tune the model to increase the accuracy to 0.5 or 1%. But the cost is like this individual model, they don't share weight anymore, right? They have large memory footprint. If you want to move these models at the runtime, it's quite expensive to do so.
Mm-hmm. So you're solving that by actually having it share weight, but is that correct? So you're putting are you putting some kind of constraints on it so that it moves as little weight as possible? Is that the idea?
Yeah, that's the idea.
Okay, but shouldn't, when you do OFA, doesn't that already share weights, or shouldn't it, like any subnetwork, like any two random subnetworks from OFA would share some weights, right? Isn't that correct?
I mean, it's true, but like, so I mean, then pretty much become this method. So we pre-select a set of subnetworks. So for the original OFA method, I think they just treat each network as individual network.
I see what you're saying. Okay, all right, yeah. So isn't it, so maybe you can also, when you do that search, so I think you just consider the latency and the accuracy. Maybe you can put a third axis on it and look at the switching time as well, right? Like that's another way to make this faster.
Yeah, thank you.
Do I mind just, do you mind me just checking my understanding?
Yeah.
So OFA is train one big model.
Yeah.
And for their original approach, it is then to extract some subnetwork using a search, and then to fine-tune that subnetwork even more to kind of improve the performance.
Yeah.
What you're doing is you're doing the first part, you're doing the search, you're not fine-tuning, which means that the remaining networks have, like, to some extent, some parameter sharing. And then, like, the way you're doing this, the dynamic switching, is you have like your original OFA model, and then you're kind of applying masks or like deleting parts in order to do the fast switching.
Yeah. I guess one more thing is different is how we do the search. So the original OFA model, original search algorithm, only using latency as the constraint, right? So if you set latency to be 60 milliseconds, you can find this point. Right? If you search, change the target to 50 milliseconds, you can also find this point. So these are easy points to find. So if you use the original kind of the OFA search algorithm, it is very unlikely you find the point on the parietal front. So what we do is we also kind of changing the search space. So if we want to find a model with higher accuracy, highest accuracy, for example, we just don't do the search for smaller models. And we also add the kind of the accuracy constraint in the search algorithm. so that we can have a library of subnetworks that have these trade-off relationships. If you use OFA original kind of the search algorithm, what you get is, for example, you can get a point cloud, right? But from this point cloud, you can also get a parietal front, but that parietal front is not as efficient as our parietal front because they don't really designed to be used to search a library of subnetworks that has the trade-off relationship. OFA is designed to find one specific model, right, under certain latency constraint.
How do you index to that library when you have two objectives to satisfy? Is it some weighted value, weighted average of the two objectives?
Sorry, how I what?
Yeah, I was wondering, how do you index to that library? So say for example, if the accuracy, expected accuracy is 74%, latency 80 millisecond for this subnet 2, how do you index to that library? That is, if it is one objective, you know that this is the particular bin that I should look at. But if there are two objectives, then how do you set the index to extract something from that library?
Okay, so after we get this library, you can see that the models in this library, basically they have different accuracy and the latency. So the accuracy is tested on the ImageNet 50,000 validation set. The accuracy, the latency is measured on the device. So at the runtime, based on kind of the latency target or the hardware available resources. So when the resources become less available, we can see, for example, a point will move to the right because, for example, on GPU, right? If the GPU is shared between between the neural network and other applications, so only part of the GPU is available to the neural network now, we can see the latency will become bigger. So if that's the case, we just remeasure the latency and switch to the smaller configuration to meet the original latency target.
Okay, thanks.
Another question here. So where would OFA stand on these plots actually?
Well, if I just show you here, it's about 1%, 1% or 0.5% here.
Oh, 0.5% here. Okay. And so is that higher or lower? What?
Higher, 0.5% higher. So basically, the model will have a similar execution time, but they are 0.5 to 1% higher accurate than our dynamic OFA model.
I see, but the drawback is that they cannot switch easily. Is that right?
Yes.
They have a big switching time between the models.
Yes.
Okay.
Are these, so you're saying the ones that are like 0.5 percentage point better, those are not necessarily the same models that you found with the that you found on this red curve? Is that correct?
Yes, from our observation, they are not the same model, but just have close performance.
Okay.
Because the space is too large, and I mean they do open source the model weight, but not the kind of the configuration. So we kind of don't know which configuration are they used to get the data.
I see. Okay, so are those like numbers quoted by them in their paper, and that's what you're comparing against when you say it's okay.
Yeah.
Lei, I also have a couple questions.
Yeah, sure.
Yeah. Okay, so I think if I remember correctly, I think the regional MobileNet V2 has like around 10 milliseconds on CPU. The latency is around 10 milliseconds. I think the models you present here are really good. They're in terms of latency on CPU. Do you have any idea, like for example, the models from dynamic OFA? Do you have some ideas like how those models look like? Like what's the building block? Is that inverted bottleneck? or just regular convolution layers?
I mean, sorry, did you mention that 10 millisecond?
Yeah, I think if I remember correctly,
Yeah.
from the MobileNet V2 original paper, there's no modifications to the architecture. I think that's 10 milliseconds on CPU. But
Well, it's
So-
probably a different CPU, right? Or
it's probably a different CPU.
differences.
Yeah. So in here, the platform we use is like NVIDIA Jetson Exivia NX.
Oh, got it.
Yeah, and also I want to say the latency here is second. It's not a millisecond.
Oh, got it. Okay. Sorry, I misread it.
So we basically remeasure every network on the same platform to get a fair comparison on latency.
Got it.
Yeah.
So regardless of the CPU version, like, do you have any idea like how these models look like? Just the architecture. Do they mostly have direct convolutions or convolutions?
Oh, I think the OFA model using MobileNet V3 as the backbone.
Okay.
Yeah.
Okay, cool. Thanks. Oh, sorry, a quick follow-up. Do you also know the number of flops and max for these models in addition to latency?
Yeah, we have it in our dynamic OFA paper.
Okay.
But what we think is like the flop is not a good representation for latency here.
Right.
If I can kind of go back to this figure, you can see that this is a kind of the universal programmable neural network. You can see it has many sub-networks, right? But based on our real measurement, so basically this figure is flops, right? But based on our real measurement here on latency, so you can see that the green line is the universal programmable MobileNet V1. Generally speaking, it has much lesser point than the kind of the flop version, because if we measure it on latency, we see many points become suboptimal, so we just take them out.
Got it. Cool.
Yeah, I think I just pulled up the paper. I think the original MobileNet V2 is 75 milliseconds on CPU and at 72 top one.
Oh, that's even more. Maybe I would. Okay. Thanks, Chai.
I'm not sure which CPU though. I think Pixel phone. Yeah. Anyway.
So the dynamic OFA is on the V2. Is that
V3? I think.
Yes, V3. Yeah, it's
V3. Okay. Thanks.
Do you have memory requirements or model size in bytes?
Yeah. So in our work, we didn't consider the memory is a big issue, but like, so I will come to this point maybe later in the talk.
So you mentioned that the biggest overhead for switching models for the original OFA is to search for the subnetworks. Is that what if one does the search beforehand and then store everything, like store the configurations of the models and then just switch according to that? Will that be faster?
I mean, well, that is very close to what we do here. One thing I want to address here is the original OFA search algorithm is not really designed to search for a library of subnetworks, because it only uses latency as the constraint, right? So even you do multiple search, there's no guarantee you find, at a higher latency, you find a model with higher accuracy, because they don't really kind of care about the accuracy during search. They only find a model that meet the latency target, and they do kind of a random search plus evolution search.
But I'm assuming in the evolution stage they have the accuracy information, don't they?
Yes, you're right, they do, but I mean, you can have well, for a given time, for a given search time, it will give the best model it can find. But that best model may not be the best model in the search space. That is what I try to say.
Sure. Yeah. I mean, in your setup, how do you make sure that you find the Pareto optimal though?
So
is
we
this
all
guaranteed?
So for the OFA, right, you can change the number of layers, channels, input resolutions, and the kernel sizes. So if we want to have a high accuracy model, we generally search the model, generally larger model, right? Model with more layers, more channels, more kernels, and large input resolutions. So we kind of reduce the search space so that for a given time, we are more easily to find a point in this region.
Okay, yeah. Same, yeah.
The OFA, they no longer share weight at the end because they fine tune it. Is that?
Yes, they no longer share weight once they fine tune it.
Okay.
Well, I remember in the OFA paper, actually, like Songhai's group actually came to our Boston office to give us a presentation on this. And they actually have two modes, right? They can either fine tune it or not to fine tune it, I remember. And if they don't fine tune, obviously they have a lower accuracy, but it seems skewed to be like, it seems the accuracy numbers still look okay, I remember. Is that the right impression? I need to look at the paper again, but.
So, I mean, even the OFA model, can run in, of course, you can use OFA without any fine tuning, but the search algorithm is still a problem, right? Because if you only search under latency constraint and in the full search space, which is 10 to the power of 19, including all the configurations of kernel, layer, channel input resolution, then what we found is that the model tend to find easy models like this low accuracy region. So if we really want to find a model with high accuracy, we really need to, first of all, introduce the accuracy as a constraint in the search algorithm. And also we needed to change the search space for this high accuracy region.
So like, how does that compare with when you do, when OFA does the evolutionary, because that would include the accuracy in the search, right? So how does that look like if you were to do that search beforehand? How would that, like, have you looked at whether your Pareto actually dominates their Pareto?
Yeah, so first of all, like so you are right, in the evolution search stage, they do also have this accuracy predictor. But what do we try to say? OFA also has a latency predictor. So these are two predictors to do faster search. But the problem is we found that this can be inaccurate. So the accuracy predictor will give you a model that is usually 3 to 5% higher than in our case, we test on ImageNet 50,000 validation data set. So the accuracy predictor is normally 3 to 5% higher accurate than the kind of ImageNet benchmark. And also the latency. Latency is normally 1.3 to 1.5 times, slower than the real latency. So, I mean,
if you're not fine tuning, isn't it like easy to query the model to actually find, calculate the latency and the accuracy when you're doing this offline search? Because you don't care about the time for that, right? So you can run this evolutionary thing and have it query. So you're not doing any fine tuning. You can just have it query the model for the actual latency and accuracy numbers, right?
Yes, but even in that case, we still need to change the design space so we can more easily find a highly accurate model.
So you're somehow changing this accuracy. So you're somehow like doing some modification to the search so that you always find the best accuracy, right? Is that right?
Yeah, I wouldn't say that we always find the better model, but like based on our experiment, if we don't change the search space, we just couldn't get the, well, if we just running the open source, the OFA search algorithm, we can never get the point, kind of the put in the paper.
I see. Okay.
Yeah.
So what do you have a slide on what changes you made to like get the high accuracy points that you got?
Yeah, we have some information in the paper. Sorry, not in the slides.
Okay, yeah, because that seems like the most important bit of the whole.
So we are currently also working on kind of. So there's another work which I didn't include in this slides, but there's another follow-on work. So basically, OFA was published in iClear 2020, and in iClear 2021 is a follow-on work called Compound OFA from Georgia Tech. Basically, they say that for OFA, right, it contains 10 to the power of 19 subnetworks, but they made some observation. So if you change the number of channels and layers together, then you can also have very good models, but the space becomes much, much smaller. So in the end, they only have 243 subnetworks. So what I would say is that, I mean, that work really kind of help to reduce the search space significantly, because if you only have like more than 200 subnetworks, you can just measure everything, right? And in once, then you get this Pareto front.
Okay, thanks.
Any more questions?
I think we should let you finish the rest before the time runs out.
Okay, thank you. So yeah, so let's talk about a little bit about the runtime resource management. So basically, this part is what we are working on at the moment, and so so I just want to share that kind of the vision of our group. So what do we think the future embedded system and the runtime management system should be? So in the past, the system is quite simple, right? You only have one CPU cores, but now you have multiple CPU cores in different types, right? Multiple GPU cores, and in the future you might also have FPGA on the fabric, multiple NPU cores, and well, you have thousands of devices and thousands of workloads. So the combination of this embedded runtime system is very complex. Managing the resources, assign a task to different heterogeneous computing cores to miss the original performance target, and also does not kind of violate the thermal or power limit. It is very challenging task. So this is a work from our, basically from the previous member from our group. It's called PREM framework. So the framework has 3 layers, right? The application layer, runtime layer, and device layer. So in the device layer, you have different heterogeneous computing elements. Right? In the application, you have multiple applications running in parallel. So this part is not is common now, right? So you have a runtime governor that can do the scheduling for the frequency and the voltage. Also change the kind of do the task mapping, right? To map the task to different heterogeneous computing cores. So what is new here is really this part. So what do we think is like, apart from changing the parameters, tweak the opportunities in hardware, we can also changing the parameters in software to reduce the computation demand of the software. So in this case, right, if we see these neural networks as dynamic neural networks, then we can just switch to a smaller configuration of network, so reduce the demand for the hardware, right? So well, obviously we don't want to reduce the accuracy for the for the model, right? But if we don't have enough resources for the model, we have to do the trade-off. And in here, we trade off accuracy for the speed up, for the energy reduction, for example. And the system also have these monitors. So the hardware monitor the power and temperature, make the system is under the limit. The software monitor basically input the requirement to the runtime. So in here, like you can say that you want a model, right? That is 75% accurate and 50 millisecond speed, right? And you can also, well, these are basically general applications. You can also include the requirement here. And the runtime manager will find a way to orchestrate all the resources in hardware and software to give a solution that makes sure try to make sure the performance is met while the limit is not violated. So, well, here let's assume a very simple dynamic neural networks. Let's see, we have a model. 100% of the model is the full model. 25% of the model only uses 25% of the parameters. Let's say this is a very simple example. So here we draw the energy and classification time trade-off on this figure. So if we are pure algorithm person, right, pure software person, what we see is 4 trade-off points, right? 4 trade-off points. Obviously, these 4 points have 4 different accuracies, but they also have 4 different energy and execution time trade-off. On the other hand, if we know nothing about the dynamic neural networks, we are pure hardware person, what we can see here is the full model, right, running on the system, and we can change the frequency and the voltage to do the trade-off. If we consider task mapping, so basically we can choose to run it on the A15 big core or A7 small core CPU. You have these 2 trade-off curves. But if we, at the runtime, we consider the both opportunities from software and hardware, what we get is this figure. You can see we have much more trade-off options, right? So if you have a point, right, if your target is 200 millijoule and 200 millisecond, the best point you get is B, right? If you have the target 100 millijoule and 400 millisecond, then the best point is A, because it gives you the highest accuracy and the lowest energy consumption. But if you only have 50 millijoule and 200 millisecond target, then you have to choose a less accurate model to run.
Why is it a U shape?
Okay, well, I mean, because this is energy, right? Because this is energy. So if you reduce the frequency at some point, because energy is time times power, right? If you reduce the frequency, the power gets reduced, but the time at some point the time getting longer. So you have this U shape.
Okay.
Yeah. And also we have we plotted some data on power as well. So as you can see here, so here we're running, if we're running the model on a single core CPU, you can see that the power does not scale with frequency, and the power scale with frequency scaling, but does not scale with dynamic neural networks. right? Because the computational intensity does not change with the network. It only changes with the frequency. However, on GPU, it's different because like smaller network does use less GPU costs to compute. That's why we can also have this power trade-off as well. So basically, if you're running dynamic networks on GPU and you switch to a smaller configuration, you reduce the power consumption as well. And here is something that we haven't done so far, but it is what me and our group try to work toward. So let me just quickly go through this example for you. So assume that you have a SoC, right, and you use our like runtime prime framework. So first, you need to kind of use the monitor to get the performance requirement and also monitor the kind of the physical limit of the system. And in here that you want to deploy a neural networks because before nothing is deployed. So you can deploy the network on NPU and use a CPU to do the kind of the co-processing, pre-processing or post-processing. And then later on, you have another application you want to deploy on the system, such as a VR, AR. Basically, they can be only run on GPU. So in here, we deploy the model, or we deploy the application on GPU with another CPU to do the co-processing. And later, now you want to deploy a second neural network because GPU and NPU are both used, right? So you can either wait for the previous task to finish, so basically not run the second neural network, or you can deploy it on the bigger cluster CPU cores with all cores enabled. But because of this, the system could quickly hit the thermal limit. So if the neural networks here, 1, 2 here, are dynamic neural network, what we can do is we change in the network to a smaller configuration, right? So we can kind of share the NPU resources. I know that this sounds like maybe a little bit crazy at this moment because the hardware really does not support such operation, right? But we have done in the dynamic OFA paper, we have done similar runtime management work on GPU. So basically, we have two dynamic OFA sharing the GPU, and in order to meet the target, we gradually changing the network configuration of the two dynamic OFAs to smaller ones, so they can both meet the latency target. Okay, so here I just want to briefly touch so what I think. So basically, it's our future work we want to do, right? So actually, I think at the moment there indeed is a practical issue of the dynamic neural networks, right? Because the inference engine, such as PyTorch Mobile, TensorFlow Lite, they don't really support dynamic neural networks. So currently we have a project running in parallel. So the project is we ask a master degree student to do some work. The work is we want to compare the execution time and the switching time of one is we running dynamic OFA in PyTorch. The second is we treat each subnetwork of dynamic OFA as individual module, as individual model. Then we use PyTorch Mobile to optimize each one of them. So basically, if we have 13 subnetworks in PyTorch Mobile, we have 13 models. But each model is optimized by PyTorch Mobile pipeline. Then we compare the kind of the switching time between the two works, the execution time, and also the kind of the total memory footprint. But this work is still ongoing, so I don't have a result to show you. Another is really to think about a better search algorithm or search space for OFA. Right? As I mentioned before, there is a a work in ICLR 2021 called the Compound OFA, which just published a few months ago. Basically, their observation is that if you scale the channel and the layer together, right, you can still have very good models, but the space is much smaller, only 243 subnetworks in the OFA model. So at the moment, we are also looking at scaling this channel layer and also input resolution. So it's like what they do in efficient net to scale these three things together. Because we think like, because based on our measurement, we compared the parietal front of compound OFA to our dynamic OFA. We found that the compound OFA still don't have this high accuracy point. So what we found is that they don't really consider the input resolution in the space. So what we are doing in parallel at the moment is we try to scale the input resolution with channel with layer to make the search space of OFA smaller, but still, I mean, good enough for our purpose. And to conclude our work, so basically we think that if you optimize a model, right, at the design time, it is not sufficient because you needed to make an assumption, right? Because if you like you say that you want to have a 50 millisecond model on pixel phone, basically you want to make sure that the frequency you choose is, I mean, can be sustainable at the runtime, right? So in order to do that, we really needed to use dynamic neural networks. So when the resources are kind of limited and not enough, we can switch to a smaller configuration. And also we think for the future runtime resource management system, we need to tweak both the opportunities in software and the hardware at the runtime together. So that, as I showed you before, the trade-off point can be much more and much more kind of fine-grained. Yeah, and this is the end of my talk. Thank you so much.
Thanks, Lei. That was a very interesting talk. Any other questions?
Could I so you say there is no inference engine. So your experiments are run without any actual dynamic DNNs then? So
no, sorry. What I tried to say that we run all the experiment in PyTorch, but what I mean inference engine is like a TensorFlow Lite, TensorFlow Lite Micro, or PyTorch Mobile. I mean these frameworks, these inference frameworks does not support dynamic neural networks at the moment.
So your experiments are actually run using vanilla PyTorch?
Yeah, vanilla PyTorch, that's right.
So it's vanilla PyTorch, so it's not actually on in like a mobile setting at the moment.
We're basically running it on Jetson platform because Jetson kind of running a Ubuntu system, so we can run the vanilla PyTorch.
And so for switching, does that work in PyTorch then, or is it still? Yeah. Oh, okay.
It works, yeah.
What kind of concurrent workload do you use to evaluate the switching?
So do you mean concurrent workload to evaluate the switching?
Yeah. So you only switch when the processor or coprocessor is busy, right? So what kind of like workload do you?
So in the dynamic OFA paper, what we tried is just running another network. So basically we run another static network such as ResNet. So basically that network we cannot change. So only thing we can change is dynamic OFA. So if that's the case, we needed to kind of using a very small configuration of dynamic OFA. But then we run another experiment. We run 2 dynamic OFA in parallel on GPU because we have 2 networks we can change. So each of them only change to kind of a middle configuration. Then that's enough for both networks.
So when you do the switching, do you have any kind of optimized way to just reload the weights that you need to reload, or do you reload the whole model when you switch?
I think as the current implementation is to reload everything, but that is certainly something we are doing at the moment.
Okay.
What do you measure to determine the switching? I guess like the current frequency or the current. How do you characterize the current workload of the process?
Yeah, here, in the dynamic OFA paper, we only do a very simple runtime. So the measurement is just the latency of that model. Right? So for example, when we start to running a dynamic OFA, let's say the latency is 50 milliseconds, and that is our target, for example. Now, when another workload is suddenly running on GPU, sharing the resources, you can see a kind of a sudden increase of the latency of the kind of the model we want to optimize, we want to measure, become, for example, 80 milliseconds. And then we gradually reduce the subnetwork, or gradually reduce the model configuration to smaller subnetworks, so that we can still meet the original 50 millisecond target. And when later on, when the kind of the second workload finished, when the more resources become available to the dynamic OFA, then you will see that a sudden kind of a decrease in the latency. So 50 milliseconds becomes 30 milliseconds. Now we can trade off back to larger model. Right? We still just need a 50 millisecond target, but now we will switch back. We switch to more higher accurate model.
Sorry. So I just want to get this straight. As of right now, though, there is no actual implementation that realizes the benefits of dynamic neural networks. Then, in that you're running on PyTorch, but each time you're switching, you're just reloading an entirely different model. So in actuality, you still have to like save all those weights separately in different state dictionaries or whatever. In your case.
Well, I mean, no. I mean, in PyTorch, you still just need to store one big backbone network, and at runtime you just switching the subnetworks.
Okay, but then you're still doing you're loading the state dictionary, so you're from storage, right? You're re-accessing all of those weights in PyTorch.
Yes, I think so.
Rather than having those there and kind of dynamically being able to just kind of shut off parts of your network, it's still a bit of a. You're not really getting the theoretical benefits right now.
Yeah, I think well, I think this is true, and I mean for all the dynamic neural network, I see that they pretty much using the similar implementation in PyTorch, and that is kind of why, because I guess this paper, they don't really do this hardware software co-design work. But in our case, we really want to do this kind of hardware software co-design. So at the moment, we try to see that whether we can kind of develop the PyTorch model to that the PyTorch model support dynamic neural networks. So we can have a implementation that is kind of really useful.
So the advantage in terms of the reloading time that you mentioned, how do you measure that? Do you have a way to measure it, or how do you? I mean, I'm just trying because if you're like really loading the entire model again, then you don't actually see the advantage that you would have in terms of loading time, right?
Yeah. So in this case, like because we think that this is just a implementation issue, so we when we say I would say the switching time, like we only consider that the time to kind of changing the subnetworks, but not not consider the time to reload the whole wait.
Okay, so you're saying just the time to reference to a new network, is that correct?
Pardon?
So you're just measuring the time to reference to this new network, right? So let's say your latency target changed, so you now have to point to a new network in the set, and that's the time that you measure, right?
Yes. Yes.
Okay. Okay.
All right, I guess it's 20 minutes overtime, but thanks, Lei. Great work.
Thank you.
If you have more questions, I can forward to him later. Yeah. Thanks.